Greetings, everyone. We are group number 23, and our problem is the one shown on your screen right now. The figure shows a passenger on a device used to produce the experience of weightlessness in a passenger when he reaches point A, which is exactly 90 degrees from our datum. In our problem, the passenger is said to have a mass of 75 kilograms, and we are asked to determine the minimum speed that he should have when he reaches point A so that he does not exert a normal reaction on the seat. It should be noted that throughout the motion, the speed remains constant. So, our first step in solving this problem is by drawing the forces acting on the man. On the vertical axis, we draw Ry and Rx on the horizontal axis. These are the forces needed for the man to move on a path following this one. One more thing that we have to draw is, of course, the weight, which is acting downward. Next, we determine our normal and tangential axis. Our normal axis is along the frame BC, with a positive direction pointing towards the point C. On the other hand, the tangential axis is perpendicular to our normal axis. At this juncture, we now have our forces acting on the man, and we can now solve for the minimum speed that the passenger should have when he reaches point A so that he does not need to exert a normal reaction on the seat. So right now, we can actually start setting up our equations of motion. Let us start with our normal axis. The summation of forces along n is equal, of course, to the mass times the acceleration in the normal axis. And in solving this problem, we choose to set our positive direction to be the one pointing towards point C, to be positive. So we now have summation of forces along n is equal to MAN. And substituting our value of our acceleration, that is v squared over rho, we now have summation of forces along n is equal to mv squared over rho. Going back to our free body diagram, we know that the forces acting on the normal axis are our weight and the normal force. So let us substitute that one in the left side of our equation. So what is left now is W minus N is equal to mv squared over rho. And since our problem states that it is asking for the speed at point A, at which our theta is equal to 90 degrees, and it is stressed out that the normal force should be equal to 0. So what is left is W minus 0 is equal to mv squared over rho. And weight is the product of mass times gravity. So we now have mg is equal to mv squared over rho. Having both the variable m at both sides of our equation, we can easily cancel it out. So what is left now is g is equal to v squared over rho. So we now have g is equal to v squared over rho. Doing a little mathematics, we could get v squared is equal to g times rho. And getting the square root, what is left is v is equal to the square root of g times rho. And in our problem, the value of our rho is equal to 10 meters. So we could substitute rho, and our Rg, as we all know, is equal to 9.81 meters per second squared. So the value of our v at point A is now 9.90 meters per second squared.